Hello, welcome to another module in this massive open online course. So we are looking at different topics and concepts in convex optimization, and particularly from an applied perspective. In this module, let us start with a new topic, and that is duality. Okay, so what we want to start looking at is a very interesting and a very fundamental concept of duality. Okay, and we have seen this to some extent. We have seen this informally. Basically what this does is it formalizes the framework of Lagrange multipliers that we have been sort of informally employing so far. So what is a Lagrange multiplier? All right, what is the significance of a Lagrange multiplier? What does it indicate? All right, and what is the formal, I mean, how do you formally define the Lagrange multipliers associated with this problem? So that is basically what we are going to see or cover now in this when we look at the concepts of duality. Okay, so now let us go back to the standard form optimization problem. Recall a standard form optimization problem is given as follows, that is, you have the objective function, let us say this is minimize g naught of x bar, this is your objective function, okay, subject to, then you have the constraints, you have the inequality constraints gi of x bar less than equal to 0, I equals 1 2 up to L, and the equality constraints g tilde of x bar equal to 0, j equals 1 2 up to m. We have seen this definition before. So these are your constraints. Okay, and of course now this is any standard form optimization problem. In addition, we have seen that if g naught is convex, all right, the objective function is convex, correct, the inequality constraints are convex, and the equality constraints are affine, it becomes a convex optimization problem. So right now this is not necessarily a convex optimization problem, this is simply a standard form, this can be any optimization problem, not necessarily a convex optimization problem. Okay, so this is, keep in mind or bear in mind, what we are considering now is not necessarily a convex optimization problem. That is the most general framework of duality, is applicable even when the problem is non-convex. Okay, and that is in fact the power, or that is in fact the appeal of this framework of duality. Okay, so this is a standard form optimization problem. Now for this optimization problem, the Lagrangian function for the above optimization problem, the Lagrangian can be formulated as L of x bar lambda bar nu bar equals the objective g naught x bar plus summation I equals 1 to L lambda I gi x bar, that is each constraint gi, that is inequality constraint gi x bar multiplied by this lambda I, which is the Lagrange multiplier, and the summation plus summation j equals 1 to m nu j gj tilde x bar, multiply each equality constraint by this quantity nu j and take their sum. Okay. Now, these quantities are the Lagrange multipliers, the lambda i's, and we have already seen this to some extent. So, these are the Lagrange now these quantities are the Lagrange multipliers. What are the Lagrange multipliers? These are the lambda i's, that is lambda 1, lambda 2 up to lambda L, nu 1, nu 2 up to nu m. These are your Lagrange multipliers. And of course, these are the each lambda I, remember lambda I is the Lagrange multiplier for your gi of x bar. Alright, we are multiplying each j of x bar with lambda I, and each nu j is the Lagrange multiplier for g j tilde of x bar. Okay, right. So, what we are doing is we are taking g naught x bar objective function plus each inequality constraint gi x bar multiplied by the Lagrange multiplier lambda I sum plus each equality constraint gj tilde x bar multiplied by the Lagrange multiplier nu j sum. So, this is a weighted sum, alright, of the objective function and the constraints, and the weights are basically the Lagrange multipliers. Okay. So, what the Lagrangian is? So, the Lagrangian, if you realize it, and it is not very difficult, Lagrangian, that is your L of x bar comma lambda bar comma nu bar, this is the weighted sum of objective g naught x bar and the constraints gj x bar or gi x bar gj tilde x bar. Okay. And now we can define that. So, this is a Lagrangian. Now, we can define the Lagrange dual function. What is the Lagrange the Lagrange dual function is gd of lambda bar nu bar. Alright. Now, remember, now this is a function of the Lagrange multipliers that you can observe. This is a function of the Lagrange multipliers. This is the minimum over x bar of the Lagrangian L of x bar lambda bar. This dual, the Lagrange, what we call the Lagrangian dual, is you take the Lagrangian, alright, for a given lambda bar, nu bar, the Lagrange multipliers, and take the minimum over x bar, alright, that is the Lagrange dual function. okay, and this is basically, you take write it explicitly, the minimum over x bar g naught x bar plus summation I equals 1 to m lambda I gi x bar plus summation j equal to, or I am sorry, I equal to 1 to L, in fact I equal to 1 to L, j equal to 1 to m nu j g j tilde into x bar, and you take the minimum of this. This is the Lagrange dual function. Okay, so GD lambda bar nu bar equals the this is the Lagrange dual function corresponding to the possibly non-convex. Remember, alright, it's important to, again I am repeating this again, it's important to remember that we have started with a standard form optimization problem which is not necessarily convex, and this Lagrangian dual function has a very interesting property. The Lagrange dual function can be shown to be concave in nature, irrespective of the original optimization problem, which need not be convex. So, the Lagrange dual function, this can be shown to be concave in nature, and this is your property. This is an important property, the GD, the dual function, and this is very easy to see. This can be seen as follows. For instance, if you look at the Lagrangian function, let us go back, take a look at the Lagrangian function, x bar comma lambda bar comma nu bar, this is equal to g naught x bar plus summation I equal to 1 to L lambda I gi x bar plus summation j equal to 1 to m lambda j tilde g j tilde x bar into nu j equal to 1 to m. Okay. And now if you observe this function, now if you closely observe this function, you can observe that even though this is a complicated function of x bar, this remember, this is a linear combination of g naught x bar, the gi x bar and the gj tilde x bar. Okay. And what are these Lagrange multipliers lambda I and nu j? Lagrange multipliers lambda i's and the nu j's are nothing but the weights, alright, and therefore it is affine in the Lagrange multipliers. Okay, and that is important to remember. If you forget, if you keep x bar constant, now here if you keep x bar constant, okay, for a moment keep x bar equal to constant. Now you observe that if you look at the lambda i's and nu j's, these are nothing but the weights. Okay. So, lambda I comma nu j equals the weights in this linear combination. Okay. And therefore, this is affine, this Lagrangian, if you look at this is affine alright, affine in the sense that it is some constant plus some vector transpose times lambda bar plus some vector transpose times nu bar. Okay, so this is affine in lambda bar nu bar, because remember we are keeping x bar constant for each x bar, for a given x bar, this is affine in lambda bar nu bar. Okay, so that is what you have to say. So for remember affine in lambda bar nu bar for a given x bar, okay, which means it is concave. Remember, any affine function, let us affine in the sense that this is a hyperplane, this is a concave function. This is affine lambda bar nu bar, and therefore this is a concave function. This implies this is a concave function. For each x bar, this is a concave function in lambda bar nu bar. Okay. And therefore, now when you take the minimum, remember what is the dual doing? This is taking the minimum. So, implies when you take the minimum over x bar. So, this is concave for in lambda bar nu bar for each x bar. When you take the minimum over the x bar, what you get is the Lagrange dual function GD lambda bar nu bar, which is naturally concave, and that can be seen simply as follows. You take two concave functions and now you take the minimum and you take the minimum. So, these are the concave functions, and now if you look at the minimum of this, the minimum is concave. Okay. So, the Lagrangian function is concave, is in fact affine in each lambda bar nu bar, which is basically concave. So, the moment you take the minimum of this over x bar, it is going to be a concave function, which means the Lagrangian dual function GD is a concave function. Okay. So, that is an important point, and again I am belaboring the point. So, GD is concave, like that is the Lagrangian dual, and this is very important, and again I am repeating this over and over so that you do not forget it, that is this is not, and this holds true even when the original problem is not necessarily convex, and that is a big advantage, because you can see, we are going to see that we are going to convert a non-convex, one can convert a standard a possibly non-convex optimization problem into a concave or an equivalent convex. Remember, concave optimization is the same as convex, because if you are maximizing a concave function, that can, we could take the negative of the objective function, you can write it as minimizing a convex objective. So, concave and convex optimization in that sense are equivalent. Okay. So, one can convert, so the power of the duality framework is that one can convert a possibly non-convex original problem into a standard form concave, or for that matter convex optimization problem, and then one can use all the tools and techniques, all right, associated with the framework of convex optimization. And this is a very powerful framework, or this is a very powerful result which has a widespread application and simplifies several convex optimization problems, or in fact can be used to simplify, also obtain simplified forms of several possibly non-convex optimization problems, as we are going to see subsequently. Thank you very much.